Consider कि ax plus by equal to c is a given straight line with c greater than 0. We are assuming, okay. So as soon as this straight line is given, this 2D plane, this whole 2D plane gets divided into two parts, this one and this one, okay. So how do we segregate, or how do we identify these two parts, and what are the constraints corresponding to these two parts? So first and foremost of all, let us concentrate on this equation given, okay. So ax plus by equals to c. That means this, from here I can get one equation or one inequality as this one and another inequality as this one, okay. So that means now we consider कि from here we are getting two regions, one this one and this one, okay. And just on the straight line it is strict equality, so ax plus by equal to c. Now which portion is this one and which portion is this one, we have to just identify from here, okay. For that we take the help of the origin, that means this point, okay. So first and foremost of all, I have said c greater than 0 for our example, okay. So now if you put 0 0 in place of xy, okay, then which of these inequality is to be satisfied? As c is greater than 0, so this inequality will be satisfied. That identifies what? 0 is satisfying this inequality, okay. So any point xy which is satisfying this inequality, let me call it say 1, which is satisfying 1, lies on the same side as the origin, lie on the same side of the straight line as that of the origin, okay. Because just see this line, with if I consider the origin as a landmark or origin as a fixed point, okay, then it raises the question whether any point which is satisfying this one lies on the side of the line containing the origin or not containing the origin, because this is the side containing the origin, this one is the side containing the origin, okay, whereas this one is the side not containing the origin, okay. So 0 is satisfying this equation or this inequality, so any point satisfying this inequality should lie on the same side as that of the origin, okay. So that means ax plus by equals to c, this inequality fits here, that is below this straight line for this case, for c greater than 0. So what is the remaining case? Ki ax plus by plus greater than equal to c is not satisfied by this 0 0. So any point which is satisfying this equation, any point xy, say I just name some x dash y dash so as to demarcate from xy, any point x dash y dash which is satisfying this one is lying in opposite side of the origin, is lying on opposite side of the straight line with respect to the origin, okay. So that means this portion ax plus by greater than equal to c is which portion? This one, okay. So this is how, given any straight line, we are dividing the whole two-dimensional plane into two parts, okay. For one it is less than equal to, for another one it is greater than equal to. Now how to segregate these two parts? It depends on the positioning of the origin. Either any point you are choosing, either it lies on the same side with that of the origin with respect to this line, or it lies on the other side or opposite side with respect to the origin corresponding to this line, okay. Again, if I suppose I have considered ax plus by c as to be positive, so suppose I have just considered c negative and ab positive I am considering, okay. If I consider like this, then and consider this straight line as this new ax plus by equals to c, then which one is the side ax plus by, as it is c less than 0, c and ax plus by greater than equal to c, just opposite, because if you now put 0 0, okay, then 0 is not less than any negative number, so 0 is not satisfying this one, but 0 0 if I put here, it is greater than equals to 0 is greater than any negative number, so it is satisfying this number. So in this case, this is the region ax plus by greater than equal to c, and this is the region ax plus by less than equal to c, okay. So again here two portions we are getting, with this one as a boundary. Okay, and again with the respect to the origin, we are determining which portion is this one and which portion is this one. So in general, we will face in linear programming problem, the constraints are given as inequalities, linear inequalities. So linear inequalities here, how we are using it? We are using it by the fact that the inequalities are generated by positioning a straight line, not of any other curve. In linear curve, positioning helps us to determine which position we are talking about or which position we are just using, okay, in the constraint. So here linear inequalities are given so as to demarcate or just represent constraints. So which constraints and how we are just representing them geometrically is completely determined in this way. Okay, so now we have the objective function in our hand and we have the constants in form of the linear inequalities, and we know how to geometrically represent them. Okay, acha, then the next point of question is that we are now, suppose we are just trying to optimize the objective function, right? The objective function, we are trying to optimize it, so either maximizing it or minimizing it. Okay, so forget about the optimization for time being. Let us talk about the feasible region first. What is the feasible region for the problem? For a given optimization problem, the feasible region of the problem is that where the xy, that is the points which we are considering, okay, satisfy all the given constraints, That means what? Suppose a very small example I am going to give. Suppose maximize x1 x plus y. Suppose it is given subject to the conditions x greater than equals to 0, y greater than equals to 0, and suppose x plus y less than equal to 3. Okay, this much I am giving. So for this particular example, as I am saying, this is the objective function. So for timing, let us keep it aside. We do not need it just now. What we need to sort out geometrically what are the corresponding regions given by these constraints. Okay, so once we consider that, then what we have to do, we just draw the 2D plane here. So once we draw the 2D plane here with x, y, so what are the constants? Now let us sort out the constants. First is x greater than equal to 0. X greater than equal to 0 means what? X equals to 0 is this line. Okay, so x greater than equal to 0 means this portion. Okay, so hold this portion. Achha, next is y greater than equals to 0. So y equal to 0 is this line, x axis. So y greater than equal to 0 is this portion. Because if you put 0 here, 0 is greater than 0, so this portion is marked here. Okay, and again x plus y less than equal to 3. So first and foremost of all, let us consider x plus y equal to 3. Okay, so x plus y equal to 3, we know how to draw it with the intercept form. This is the 3, it is just intercepting at the point 3, 0 and here at the point 0, 3. Standard form, we all know it. So this is the line x plus y less than equal to 3. So what is the region x plus y less than equal to 3? Let us take the help of the origin. For this is a standard, we already know that this is the upper portion of the x axis and this is the upper portion of the y axis. So we are considering the which one? First quadrant or for the positive quadrant. Okay, and for this one, let us take the help of the origin. Okay, so if you put 0, 0 here, 0 is less than 3, x plus y, that is 0 is less than 3. Okay, so any point which is satisfying this inequality is lying on the same side as that of the origin with respect to this line. Okay, so x plus y less than equal to 3 is which portion? It is this portion, that is on the side containing the origin portion. That is only one thing we have to just keep in mind regarding this, ki either side containing origin or side not containing origin. Any inequality if you want to just determine. Only these two portions, only these two things we have to keep in mind for justification, which is the region given by the constraint, linear constraint provided. So here in this equation it is given x plus y less than equal to 3. So side containing the origin is this one. So side containing the origin is this one. Okay, so we are considering this one here. So now you see, as we are talking about the feasible region is the region, roughly speaking, region which is satisfying all the given constraints, okay. So here, what is the feasible region in this example? The feasible region, if you just can make out, is this portion on this side, and again here this side, okay, and here this one. So ultimately this portion, let me just name it OAB. So OAB is your feasible portion or feasible region, where this constant and this constant all are satisfied. Okay, so this is the feasible region for the given problem. Okay, so here we are getting the feasible region. Okay, so it may happen, or it may just seem obvious कि okay, any problem is provided to us, we will always get some feasible region. But no, that is not the thing always. Okay, in general, for example, suppose consider कि x less than equal to 3 and x less than equal to 3, and then I take y greater than equals to 2. And let me just take in terms of x only. Just let me just take this one. So suppose I am taking, okay, so x greater than equal to 5 and y say only greater than equal to 0. I am just putting these three constants all together. Let me just put these three constants all together, and you are just maximizing the same given function x plus y. So forget about the objective function, let us think about the constants first of all. So y greater than 0 means this portion, okay. X less than equal to 3, so x equals to 3 means a fixed straight line here parallel to the y axis. So x equals to 3 is this one. So x less than equals to 3, so if we put 0 here, so 0 less than 3, so this one, okay. So if this and this are the constants, then this is the feasible region, this one and this one. But there is an extra one here, a is greater than equal to 5. So again we have to consider the fixed straight line parallel to the y axis as this one, x equals to 5. Okay, so x greater than equals to 5 means origin is not, if I put 0 here, 0 is not greater than 5, so it is on the other side of the origin. Okay, on the other side, not containing the origin. Okay, so this portion here, this portion. So now you can easily see that this portion, this region and this region so far are not at all intersecting, they have nothing in common. So in this case there is no feasible region, because all the constants cannot be satisfied simultaneously. All the constants here not satisfied simultaneously, so no feasible region. For here we cannot try to find out the solution of this given optimization problem. Okay, so this is an example of no feasible region existing. Okay, so this depends on the problem which is given to us, whether the feasible region exists or not. Now once it is we are ensured that the feasible region exists, then our question comes to, okay, then maximize the objective function if it is maximized, or minimize the objective function if it is minimization problem. So now what we have to do, we have to find point, I am writing as say x0 y0 belonging to the feasible region f, I am writing feasible region such that the optimization function is z, I am writing as z, the objective function, obj function. Okay, z at the point x0 y0 is the maximum of all possible values of z from the feasible region, all possible values of z from the feasible region. Okay, it has just been it, of possible values of z from the feasible region, Okay, so this one is that we are trying to perform the actual function of optimization, and before this we were actually trying to find out the feasible region. So once we know that feasible region is there, suppose this is my feasible region, so suppose this one is my feasible region, then say A, B, C, D is a feasible region, then from here we are trying to find out the point x0, y0 such that z of x0, y0, in case of it is a maximization problem, z of x0, y0 is greater than equal to z of any other xy, from the feasible region. xy, x0, y0 all belong to the feasible region. Okay. So for that, what is the standard technique? According to the theory of the linear programming problem, the standard technique is that is this x0, y0 will correspond to one of the intersection points of the constraints. Actually, this x0, y0 will be provided by one of the extreme points of the feasible region. So x0, y0 in general, I am not speaking of any specific problem, provided by one of the extreme points in case it exists. As I already gave an example of non-feasible region, so in that case it doesn't exist. So if it exists, it is provided by one of the extreme points. Okay. And how do we search for it? We search for it by just checking first the points of intersection of the constants. These are the constants. This line is the boundary. So this is given by the constant. Again, this is given by another constant. And this is given by another constant. Okay. So all these are the constants. Okay. And so any point you take from here are the just lying on the boundary points. From all the boundary points, we are just concentrating on the intersection of the constant. That is the intersection of these lines. Okay. We will check the functions. So suppose I will check z at the point A, at the point B, at the point C, at the point D, and then I will just judge which one of them is the maximum. Then that will be the maximum value of the objective function, and corresponding, say suppose B is occurring the point where ZB is the maximum value given, then B is the point called the maxima. Okay. Similarly, in case of we are considering the question of minimization, just the reverse thing we have to do. We have to find out this again, this feasible region, and along with we are just finding out the points of intersection of the boundary lines, that means the constraint lines, and then we are just trying to find out z at all those points, and then we are checking which one of them is the minimum, and that will be the minimum value. So z mean will be in that case, in case of z max, and the point for which this minimum value is obtained is said to be the minima. Okay. So roughly speaking, this is a standard technique which we follow for our optimization problem. Okay. And another thing also happens. In fact, here we are saying we are getting one point where you are getting the maximum value. It may occur your maximum value is occurring, or your minimum value, that means optimum value is occurring at more than one points. Optimum of z occurring at more than one point. Okay, from the feasible region, belonging to the feasible region. This is a case of alternative optima. Okay. This depends on the problem. Obviously, we are not going to just consider any further case from this side. If it occurs within our just any problem we consider, we will just say it. The main thing is that alternative optima is that, so suppose in this figure only, suppose consider this figure only, say BC. Okay, suppose it is the case ZB equal to ZC. That means what? And both of them are greater than ZA, ZD. Okay, and as we said, we already know this extrema, if it occurs, that is the maxima, that is the point where it will just take the maximum value, will come from this boundary points only. So we are not considering any point from inside for this checking the maxima or the minima. Okay, so for checking the maxima or the minima, we are considering the boundary points, and once we are considering the boundary points, the intersection points further of the constraints, and once we are checking the intersection points of the further, so suppose there are 5 or 6 intersection points, then we are just comparing among them only. No further we are looking for any interior point from inside or any other boundary point from here, or here. No. As the theory just predicts, this will be given, the extremum value will be given by the intersection points only. So we are now just concentrating on the intersection points only. And now while concentrating on the intersection points, if it appears ZB greater than equals to ZA, ZD, and again ZC greater than equal to ZA, ZD, and this two equal, then what does it imply? Ki B is a maxima and again C is also maxima. Okay, that means B and C are alternate maxima. That means you can consider this also, or B also, or C also. So they are alternate maxima examples. Similarly, for the question of minimization, the same thing, only the minimization technique to be kept in mind. You have to find the minimum value. Okay. So that is the case of alternative maxima. Another thing that may occur, and sometimes it also occurs that throughout the entire constraint line, the extrema exists. That means throughout the entire boundary, the extrema exists. Then also, that means what? So suppose here only, throughout this line, any point you are taking, so suppose Z, I like that Z lambda, okay, so as to indicate that lambda is any point belonging to the boundary AD, okay, for Z lambda is greater than equal to any Z value you are taking, ZA, ZB, ZC, ZD. That means what? Throughout the entire line you are finding the maxima. That means this is also an example of infinite number of alternative optima to exist in this case. Okay. Another one is the unbounded solution. Unbounded feasible region, in fact. Unbounded feasible region. So in that case what happens actually? Here, just if I consider this figure, what is happening? The feasible region is forming a closed bounded region, right? A, B, C, D, this square shaped figure we are getting. Again, here we may have got like this also. So suppose some boundary is there which is bounding or restricting the growth of X or the growth of Y from all sides. Okay. So suppose this is your X increasing region, this is your Y increasing region. Suppose ultimately by solving all the constants we obtain this one as the feasible region. So you can see once and only we get restricted within this region, my X cannot increase infinitely. Like this it cannot increase. Again my Y cannot increase infinitely. It will remain confined up to this maximum height, this, and X will remain confined up to the maximum height, this one. Okay. So this X and Y is restricted in case we get this boundary from all sides. Okay, so this is the case, X and Y restricted when the feasible region is bounded, FR is bounded, but it is not always the case. For example, so suppose I give one specific example. Let me just give one example only. X less than equal to 3 and Y greater than equal to 0. Only this much I give as a constant. Then what? If you draw the lines, what are just constants, what are you going to get? Y greater than equal to 0. So above the x-axis you should remain, okay, no problem. So the whole plane is coming. And now let us take the intersection with this portion, which this portion means first I have to draw the x equals to 3 line. So let me draw that line, x equals to 3. Now anything which is less than equal to 3, that means 0, this origin is satisfying this one, 0 less than 3. So x less than 3 is which portion? Containing the origin portion. So this one. So now you see, for the feasible region, we know this should be the intersection of this constant and this constant. So according to this figure, which is that given by? That is given by this portion, you see. This one in total. This will go on increasing. Okay. So no matter how you are just approaching, this will just go on. Just this is the boundary on this side and this is the boundary on this side. So this one is going like this. Okay. You just can take anything from here. Anything and everything from this side. So this is unbounded. As here, your x we can be anything tending towards minus infinity. Anything less than 3 is possible. Okay. And y, anything positive is your possibility. So y is going on increasing or diverging towards plus infinity. So obviously it is the case of unbounded solution. Again it may happen that y is restricted or x is restricted and one of the coordinate or the axis is increasing towards plus infinity or minus infinity. Then that is also a case of unbounded solution. Okay. For suppose I put another constants here only. So suppose y greater than equal to 0, y less than equal to 4. So that means what? An extra constant I am providing. So suppose this one. y equal to 4, so y less than equal to 4 means this one. So what, your y's increment is restricted, but your x is still going on in decreasing, so that means here it comes like this. Okay, so ultimately your feasible region is given by this portion, this parallel band, the C here, it goes on increasing like this. Okay, so here x becomes unrestricted, by y is restricted. Similarly, it may happen that x becomes restricted and y becomes unrestricted. So if at least one of your abscissa or ordinate becomes unrestricted, then you are getting unbounded feasible region. And from there also we can try to find out the maximum of the objective function or the minimum of the objective function. It may occur from there. It may occur that the z max or the z mean is itself unbounded, or it may happen that they are bounded real numbers. It depends on the question. Okay, whether your z max may be bounded, that means some finite real number, or it may be unbounded, that means you cannot get any finite real number so as to claim z max equals to that much. I cannot claim like that in this case. Same is the case for z mean if it is a minimization problem. Okay, so these are in short the gist for doing the LPP part. So let us now go back to the original material here. Okay, so let us now consider a specific problem, the carpenter's problem. Okay, so this carpenter's problem we have already dealt once. We have just tried to do in the previous lecture the optimization overview part. So that problem only we are now considering. Here the carpenter is making some sorts of goods here, wooden goods, along with some sort of resources available to him, and also some labor problem is there. So with all this constant, let us see what we are trying to optimize here. So consider the version of the problem introduced in section 7.1, that is the previous one. The carpenter realizes a net unit profit of $25 per table and $30 per bookcase. So these are the two quantities he was making. Two things there he was making. Okay, table and bookcase. Okay, so part table he is going to make a profit of $25 and part bookcase $30. Okay, he is trying to determine how many tables x1 and how many bookcases x2 he should make each week. Okay, so the time period is each week, 1 week. Okay, he has up to 690 board feet of lumber and up to 120 hours of labor to devote weekly to the project. So these are his resources. Okay, so the lumber and the labor can be used productively elsewhere if it is not used in the production of tables and bookcases. That is the future use is also a possibility. We have to keep that in mind. Okay, he estimates that it requires 20 board feet of lumber and 5 hours of labor to complete a table, and 30 board feet of lumber and 4 hours of labor for a bookcase. Okay, so what he tries, obviously he tries to maximize his profit. Okay, so that means per bookcase and per table he is making a specific profit. What is that? $25 per table and $30 per bookcase, and x1 is the quantity number of table he is making, and x2 is the number of bookcases he is making. So 25 x1 plus 30 x2, this is his net profit function, P function, if I say profit function. Okay, so profit he will try to maximize, obviously. So what is the control factor? x1 and x2 he can increase, but he cannot increase unboundedly. There are some restrictions we maintain. There is a restriction of the labor available to him. There is a restriction of the material available to him. So those two restrictions he has to satisfy. So those are coming in the form of the constants here. So first let us see the lumber restriction. There is the material restriction. What is the total amount of lumber present with him? 690 board feet. Okay, so 690 total, and then how much he is requiring per bookcase or per table? Per table he is requiring 20 board feet. Okay, so 20 into x1, and per bookcase 30 board feet. So 30 into x2. So 20 into x1 plus 30 into x2 is the total requirement of his. Okay, so this should not be exceeding 690, and also not strict equality is taken here. Why? Not strictly strict less than you can just say not strict equality is taken here. That means I am not saying it 20 x1 plus 30 x2 equals to 690. This equal to is not taken here. Why? This is because of the case this future use is one possibility which we have to keep in mind. If it is not the case whatever is present with him he will use it totally. it may happen that some amount of lumber remains after he finishes his work, or some amount of labor is there which he can still use. Okay, so that means what, for the lumber here 690 is the maximum, so whatever he uses that should be less than or equal. If it is equal to, there is nothing left. If it is less than, then there is something left which he can further use for in future. Okay, so that's why this less than equal to is taken here. Okay, next we have to consider the labor. Okay, so the labor, how much is required for part table? Part table, it is required 5 hour of labor to complete a table, so 5x1, and 4 hour of labor to complete a bookcase, so 4x2. So again 5x1 plus 4x2 should be less than equals to 120. So that is what we are given here, and this constant is quite obvious because x1 x2 you are considering to be the quantities of the table and the bookcase is made. So definitely there should be positive quantities, or at most it can be equal to 0. Suppose he cannot make any bookcase with whatever resources is present to him, then in that case x2 is 0, or same can happen with x1 equal to 0. So in general x1 greater than equal to 0, x2 greater than equal to 0. So these are the 4 constants which we are getting for our problem, and it is a maximization problem. So as we said, what we have to do, we have to first sort out the constraints, we have to first find out the feasible region if there is any, and then we will try to find out the point of intersection of the constant lines, and for the point of intersections, whatever point of intersections we get, for each and every one of them I will determine the value of the objective function, and then I will check which one of them is the maximum. That will be your maximum value of the objective function, and corresponding point for which I am getting the maximum value, it will be my maxima. That means x1, so suppose x1 x2 we are getting, so suppose I am giving an example 10 30, then 10 pieces of here table and 30 pieces of bookcases he can make, so as to get the maximum profit from the given resources. Okay, so let us see first how they are doing it. Okay, so for this one, see here, so what are the constant? This is the constant one, 20x1 plus 30x2 less than equal to 690. So this line is the constant here. So I am just drawing it roughly so as to just segregate whatever this feasible region they are getting. So this one you are getting to be this line 20x1 plus is the constant one, I am writing C1 in short. Okay, and then is the constant C2, 5x1 plus 4x2 less than equal to 120. So this one, suppose I've just drawn a bit. Okay, let me just draw it like this. Okay, so this one I am getting. Now what is the constant? This is the constant line I have drawn, but what about the region? What is inequality? Okay, so 20x1 plus 30x2 less than equal to 690 means what? If you put 0 0 0, that means 0 less than 690. So this one is containing the origin. So which portion is given via this line? This portion is given. For this one, this portion. Okay, another thing obviously coming, x1 greater than 0, x2 greater than 0. So that means you will be above this line and on the right hand side of this line. Okay, and last one is this constant C2. For this one, what is the restriction? It is saying 5x1 plus 4x2 less than equal to 120. So again, if you use origin, then this constant is the portion containing the origin. Okay, so again that is given by this one. Okay, so ultimately what you are going to get? You are going to get this and this much as your feasible region where all the constants are satisfied. So that is here indicated. Okay, so once you know okay, there is feasible region, so first portion of our work is done. Okay, feasible region is there, then we can search for the optimum value. Okay, first that thing, and then once feasible region is there, let us just find out whether it is bounded or unbounded. Yes, it is bounded because you are getting a closed figure here. Okay, that is the point. There are intersecting points for each and every of the every pair of constants you are taking. If you are taking these two constants, then they are intersecting at this point. If you are taking these two constants, then there is an intersection point. If you are considering this and this constant, then again there is an intersection point. If you are considering this and this constant, then again there is an intersection point. So in short, we can just think of like that also, how we are going to determine whether it is a bounded feasible region or not. In that case, each and every pair of constant lines you choose, they should be intersecting. Okay, so here that is occurring. So this is a bounded region A, B, C, D. Okay, so A, B, C, D is my bounded feasible region in this case. Now in the next activity, find out the extrema point, that is the point of intersection, not all extrema points, but the points of intersection of these inequalities, or sorry, for the constant lines. Okay, so one is the origin, another one is 24 0. Obviously you just, how you are finding this out, you are finding out by just putting here, it is cutting the x1 axis, that means x2 0. So x2 0, if you put here, you will get x1 equals to whatever is 24, so 24 you will get here. This you have to just determine in your own. And again for this line, it is cutting the x2 axis, so x1 0 here, so if you put x1 0 here, you will get x2's value. So this is 23, 0 23. And for this one, you have to just solve the equation 5x1 plus 4x2 equals to 120, and 5x1 plus 4x2 equals to 120, and this one 20x1 plus 30x2 equals to 690. Once you solve this two, you will get this point C. Okay. So once we are done with it, then what we will do? We will find out, say Z is my objective function, I will find out ZA, I will find out ZB, I will find out ZC, I will find out ZD. Then I will compare. Okay, the extreme point I will consider, and then I am just comparing. So if an optimal solution to a linear programming exists, it must occur among the extreme points of the convex set formed by the set of the constant, as I already said. The optimum value will be coming from the extreme points only, not from any interior point. Okay, it is impossible according to the theory. Acha. Then the values of the objective function for the, that is the profit function for the Carpenter problem, at the extreme points are this one. So A means 0 0. What is the value coming? 0. B, that means 24 0. What is the value coming? This one, this one. This you have to calculate. Nothing to say about it. Okay, you just calculate, just putting this x and y in your objective function. That means this one which is given. Okay, this one which is given, you just put it here and find out the corresponding maximum values. Okay, so once you find out, you enlist it here, that means list, make a list here. So out of this, which one is the maximum? 750 is the maximum. Okay, so obviously it's a maximization problem, so I will take this 751. So Z C is the maximum. Okay, so which one is your maxima? Maxima is 12 15. So x1 equals to 12 and x2 equals to 15. That means the carpenter can make a maximum profit of $750 by making 12 tables and 15 bookcases. So that is it. Okay. Acha. So this is how we just do one just physical problem which is given to us. Okay. Now let us recall back the problem which we started with the finding the curve fitting problem, actually linear curve fitting problem, for which we were using the minimum of the maximum. That is, we minimize the maximum of all the deviations. Okay, so that's what we are just recalling back here, which we use in the first part of the lecture. So this one was the data table given. Okay, so y equal to cx is the curve fitting. Okay, curve fitting we are using here. So linear curve, so c is the unknown constant, as c we have taken to be greater than 0. Okay, and we have already deduced the constants for this equation. Okay, and also the objective function we have sorted out. What will be the objective function in this case? Okay, so now let us start the LPP problem here. So what we want to do here, we wish to find out a C such that the resulting largest absolute deviation R is as small as possible. So that means actually we have to minimize R, okay, subject to all these constraints, 6 constants, because there are 3 points. For each point we were getting 2 constants as discussed before, so 6 constants are there. Okay, another thing is that minimization of R we are considering. Okay, so what we have to do here, again we have to find out the feasible region. Okay, so for that we have to decode all these constants given. So here what are the parameters? R and C. Okay, R is one variable and C another variable. So C we have taken along this axis and R we have taken along this axis. And R we, what was R? R was maximum of all I Ri, where Ri was yi minus y of xi. So obviously R is positive. Okay, so no question of just searching for minimum value of R below this C line, because R is always positive. Okay, so we are showing only the this above portion of the C line. See, I am not considering this portion anymore. Okay, another thing is that I have taken C greater than 0. That means I am considering this portion. That means if we consider the 4 quadrants, this is R, this is C, then obviously as R is greater than 0, I am restricting myself towards this part, and again c is greater than 0, so I am restricting myself towards this part, this one. So what is the common region? This one is the common region. So the first quadrant is the common region. So this first quadrant is shown here. No other quadrant is shown in the figure. Okay. Now once that is sorted out, let us now sort out the constants which are given. So each and every of this constant, as I already said before, are linear constants. So obviously they are linear curves only, that means the straight lines. Okay. So again, by using the intercept form of the straight lines, we can simply find out the constants. First we have to draw the straight lines, then we have to determine this constant region. So first it says suppose r minus 2 minus c equal to 0. Okay. So r plus c equals to 2 actually. This is one straight line. So that is given by this intercept 2 intercept. So this is your constant 1. Okay. And again another for this one, r minus c equals to minus 2 is a constant. Okay. So for the constant 2, this is the constant 2. Okay. Okay. That means here it will be making a negative intercept on this line, on the r axis. Okay, so whatever, this already you know, I am not going into that. You can obviously draw at least the straight lines in the intercept form. Okay, so once you draw the straight line, let us just determine the inequality portion. So first and foremost of all, for r plus c equals to 2, then we are given the portion r plus c equals to 2 form. I am just saying from here. So r plus c greater than equals to 2 is the region there we have to consider for the constant given. So if I put 0 0, so 0 is not satisfying. So this region is the region not containing the origin. So which portion we should take? We should take this portion. That's what they have taken. See, this portion if I take, this is not containing the origin, because side containing the origin is just the opposite one with respect to the constant one. Again for constant 2, r plus 2 minus c should be greater than equal to 0. So if I again put 0 0 for r and c, then you are getting 2. Then 2 is obviously greater than 0. So obviously this constant 2 is the portion containing the origin. So if I consider this as a constant 2, so which portion should come here? Containing the origin, this portion, here, because here only this containing the origin will come. Let me just try to show it here in case if it is not clear to you from this figure itself, because many lines are put all together, so it is becoming a bit clumsy here. Okay, I am just trying to give idea with a few lines only. Let us consider the second constant only. Okay, so now your second constant I am just considering. So 2 this point, so 2 this point, this one, and like this is your second constant, right? Okay, so if this is my second constant, I am just considering about this positive quadrant only, not thinking about anything else or anything beyond it. Okay, so this is a positive constant, this is your line which is given. Okay, so now I am trying to find out the portion or the region indicated by constant 2, that is indicated by this straight line, but containing origin. That is which portion it should be. So origin is on this side, so this portion is the portion which should be taken with respect to the straight line corresponding to the constant 2. That means with respect to the straight line r plus 2 minus c equal to 0, this should be the region corresponding to the constant 2. So that is what is indicated by this arrow. Here what they are doing to make this figure less clumsy, they are giving just 1 or 2 arrows so as to indicate which portion or which side you are considering as the constant by the given equation or by the given inequality rather. Okay, so constant 2 is this portion, that's what they have marked here. Okay, similarly for constant 3, constant 4, constant 5, constant 6. Okay, so for constant 3, suppose r plus 2c greater than equals to 5. If you put 0 0, okay, then minus 5 is not greater than 0. So again this one is the region not containing origin. So r minus 5 minus 2 plus 2c is which line? Constant 3 line. So this one is your line. Okay, so not containing the origin means what? Containing the origin with respect to this straight line is this portion. Okay, but they are not containing this side, so I am taking this portion. That's what they have claimed here. Again for constant 4, 5, 6. So ultimately if you plot all the things, then you are going to get this as your feasible region. This shaded region is your feasible region. Okay, so this one, after plotting all the constants, this one is coming as a portion which is satisfied by all the constants along with the fact that r is greater than 0 and c is greater than 0. Okay, so once we get that, what is our next? So once we get that, we are ensured okay, feasible region is there, then we can search at least for the optimum value. Okay, so that is an indication. So once we do that, what is our next criteria or next activity? Let us find out the points of intersection. Okay, so here the points of intersection is provided by this point A. Okay, let me just rub it out here, whatever extra thing is there. Okay, then this is the point, one point coming here A. Okay, then here this is a boundary, you are coming along the boundary, and this is the constant line. So this one here again is the point. Okay, so this portion B, so actually the curve is, that is the feasible region is looking like this one, then this one, and then this one. This is your feasible region actually. So A, then B, then C, and ultimately here there is no such thing which can bound, so it goes on. Okay, it goes on moving. Okay, so at A we will find out the value or the function. First of all, what is the point A that you should demarcate? Again at B, C. Okay, you have to find out the functional value, that is a function of the objective, the value of the objective function we have to find out. Okay, so I am not going to just go through these things, I have already said. Okay, so this is what they are doing. So A, B, C, these are the three extreme points which you can just see as the boundary points. Okay, so I am just going to find out the objective function value at these points only. So what is my objective function? Fr equals to r. So this is the given by the ordinate here. Okay, so at A it is 8, at B it is half, and at C equals to 1, it is 1. How it is we are getting it? We are getting just by as we did before. For A, how it is, what is the point A? It is the point 8, 0. Sorry, 0, 8. Okay, at the point B, B is the point of intersection of which one? Constant 2 equality, that means constant 2 straight line, and this one, that is constant 5 straight line. So if you just find out the intersection of these two straight lines, you are going to get the B. They have obtained it as 5 by 2, 1 by 2. Okay, and then again C, it is given by the intersection of constant 2 and constant 4, and also I think constant 6 also. Okay, so no need of taking 3, it is enough to take 2. So constant 2 and constant 4. Okay, so constant 2 and constant 4 we are getting here. Okay, so once we take that thing here, constant 2 and constant 4, here it is written. Okay, acha, so that also is given to be 1, and 5 by 2, 1 by 2. So 1 by 2 is the ordinate, so half, and for this it is 1. Okay, as it is we are getting C as 3, 1, so 1 is the ordinate here. So as is you are going to just maximize Fr equals to R, that is you are going to maximize the ordinate only. So you are given by this ordinate value at the corresponding extrema values only. So out of this, which one we will need now? For our, what is our purpose? Our purpose here is just minimization. Okay, we are trying to minimize the deviation, because then only the corresponding curve will be the best fitting curve. Okay, so here which will serve our purpose? B will serve our purpose, because B is giving you half, the minimum of all these three. So that is what they have said. The extrema point with the smallest value of R is the extrema point B with coordinates 5 by 2, 1 by 2. Okay, the C equals to 5 by 2 is the optimal value of C. This is required because we are trying to find out y equals to Cx. Once C is known, the curve is known, otherwise it is unknown. So C is our requirement here. So corresponding C is taken from this point B values abscissa. Okay, so 5 by 2 is taken from here. From here 5 by 2 is taken. So C equals to 5 by 2. So your curve, best fitting curve, linear curve is given by y equals to 5 by 2x. So that is what they are given. And what is the deviation in that case? If we consider this, then according to the thing, it is given by the R of B. Then what is R of B? So R max here is half. Why R max is written? Because just recall back how we designed R. We designed R to be the maximum of all Ri. So that's why they are saying R max. That means maximum over all Ri is half here. So R max is half here. Okay, so that is the thing we have just obtained from here. Okay, this model interpretation part you may skip here also. This is that whatever we have interpreted here, they are just now again showing it by showing the residual values. That is they are considering R1, R2, R3. For example, this one 5 by 2 minus 2, that means 2 is whatever it is coming from the data points. But the data points, if you just recall back, what are the data points here? The data points were given by like this. Okay, so the data points here was given by this one. See here 2, 5 and 8. Okay, so 2, 5 and 8 correspondingly here are shown 2, 5 and 8. Okay, so this one is 1, 2, this one is another 5 here corresponding to this point. Okay, and 8 here is another point 3, 8. So this 1, 2, 2, 5, 3, 8 are coming from the curve or coming from the points itself. That means if you plot the point, this one and then this one are the points which are given to you, and the straight line is suppose coming like this. Okay, so I think one is matching exactly, while others are just on this side or on that side. Okay, so here you are just measuring how much you are getting the residual or the Ri actually you are showing in this figure. R1, R2 and R3 specifically you are showing in this figure. This already we have discussed before how you can show this Ri. Just you have to take the yi minus y of xi. So as you know y equal to cx now, y equal to 5 by 2x. So you have to just calculate it. Okay, once it is given in the question, suppose, let me just show it separately instead of going into this figure once again. Let me just show it separately in general. So suppose I have obtained my data curve, the most befitting data curve is y equal to 5 by 2x, and my points are given as x, y, as I'm just not going into all those specific points, x1, x2, y1, y2, x3, y3. These are the 3 points which are given. So what is my activity now? I have to plot this one first. So just keep in mind it is passing through the origin. So whatever, you know how to draw this curve. It is up to you how you draw it. Obviously you have to draw it accordingly. I am not going into that part. So once you have, suppose this is the line which is coming for this one. Okay, so once we are done with this, then what we have to do, we have to find out the y of x1, that will be 5 by 2 x1. Okay, so one point will be, you have to actually plot here 6 points. Why I am saying 6 points? First you will plot this x1 y1, x2 y2, x3 y3. Plot this one first. Plot. Okay, so suppose this one and this one here is your x1. Say I am just naming it. So p1, it is p2, it is p3. Say p1, p2, p3. I am arbitrarily drawing. Okay, I am not drawing accordingly whatever is the value given in the example discussed. Just simple, I am just trying to make it. So p1, p2, p3 I am given, and another 3 points you will have to draw. Total 6 points. What are those 6 points? Coming as x1, y of x1. Okay, that means x1, then 5 by 2 x1, and then x2, 5 by 2 x2, then x3, 5 by 3 x3. 5 by 2 x3. Okay, so this one we will say, suppose q1, this is q2, this is q3. All these points are which points? They are lying on the straight line which you have drawn, y equal to 5 by 2x, straight line L I say. So L. So suppose you are just getting this one as your point, this one as your point, this one as your point. Okay, so now what we will do, you will just consider this distance here. Again you will consider, say suppose this is the point, this is the distance here, again this distance here. Okay, so this is the residual which will be coming. Another thing, these points obviously will be just either above p1 or below p1. Okay, let me just draw it more appropriately, because they cannot be anything arbitrarily once you fix it, obviously. So p1, p2, p3 was this one though. So for p1 you are getting correspondingly x1 5 2 by 2 x1. For this point, if I follow the curve, it will be on this one. So suppose here, either here. So this is the residual distance in this case. Again for p2 it will be here. Okay, so this is the residual distance in this case. Again for p3 this will be here. Again this is the residual distance in this case. So here you can measure what is the value coming. Here also we can measure what is the value coming, simply by just finding out the distance between y1 and 5 by 2 x1, and then y2 5 by 2 x2, and then y3 5 by 2 x3. Okay, so just you can measure all of them, because all of these are now known real quantities. You can measure them, you can put the values, and you can just simplify to get the real quantities results, and you can say which one is greater and which one is lesser and which one is the maximum of all this, and that should match with your whatever you have obtained in the LPP problem. Okay, So that is the thing they are discussing there. Okay, so let us go back here. And empty and unbounded feasible regions I have already discussed prior to this discussion, so I am not going into that part again. Okay, this already is giving some just constraints which are incompatible. That means no, obviously we will not get any intersection region of these two type of constraints. Okay, so in that case we will get no feasible region, as I already said. An unbounded region, obviously I have already given this example itself is an unbounded region example which we just did here. This is unbounded in this way. But see here, one thing you note here, what this is an unbounded feasible region problem, but for our purpose of optimization, is it creating any problem? The answer is no, it is not creating any problem. Why it is not creating any problem? Because what is our optimization goal here? To minimize the R, that is to minimize this height. That's why this height is increasing, going on increasing infinitely, but it is not restricting us. Actually we are trying to go down and down, as much down as possible, because we are trying to minimize his height, and the unboundedness is coming in terms of the increment of the height. That's why there is no problem with it. But suppose if the problem was posed like you maximize R, then in that case you cannot find a bounded solution. You cannot find a bounded optimum or maximum value if it was a maximization problem. Okay, so this being a minimization problem, it is not creating any problem, because we are trying to find out the minimum. What is the minimum height from here? What is the minimum R? How much small I can take here? That is our goal here. So no question, no problem if it is going on increasing, the feasible region is going on increasing on this side. But if it was a maximization problem, then definitely it is a problem. Where to stop? There is no boundary, there is no stopping point, so it will go on increasing. So there is ultimately no bounded optimal solution in that case, no bounded optimal solution in that case. Okay, so this is also a specific or classic example where unbounded feasible regions, in case of unbounded feasible regions also we can get bounded optimal solution. So this is a perfect example for it. Bounded optimal solution coming in spite of the feasible region itself being unbounded. Okay, so let us stop here up to this. We will continue for the rest part in the next class. Okay.